Hi everybody, welcome to another video in differential equation, section 6.1. In this chapter we study linear equation again, but this time in more general, we extend the equation into the n-order linear differential equation. So if we have the n-order, we go up to n-order of derivative all the way back to the first derivative and then the function. To go with that, by the standard form, the first coefficient is 1 for the n-order derivative. Everything after that we have the coefficient as a function of x equal to the input function g of x. If this is equal to 0, we have a homogeneous linear n-order equation. If we have an input function here, this is non-homogeneous equation. And the existence and uniqueness, all we need is that all of those coefficient function and the input function continuous on the interval that contained in x0. X0 is the initial values at the initial point where we have the initial values, initial conditions are given. Right. So, and that is the existence and uniqueness. We just need to have all the coefficient function and the input function continuous on the interval that containing the initial point. In that case, doesn't matter what the choice we for the initial condition. The solution exists and is unique. Right. Linear independence. Of course, we define this way back in chapter 4. Now, if we have the function f1, f2 all the way up to fn, and this function we have derivative up to n minus 1 order. So function first derivative, second derivative, all the way to n minus 1 order derivative. In that case, there are n rows, n columns, so we have a square matrix. For the square matrix, if we find the determinant, so that gives us the wrong skin. So the wrong skin of the function f1 all the way to fn, where x is a variable, so that is the notation, equal to the function all the way up to the n minus 1 order derivative. Determinant is the wrong skin. Right. So of course we use that to determine if it is linearly dependent or independent. Right. Linearly independent. Right. First we define linearly dependent, which is opposite to linearly independent. So linearly dependent, we have this function as linearly independent, linearly dependent. If one function can be expressed as a linear combination of the other, meaning that if we have the linear combination of all of those functions and that combination equal to 0, not all of them are equal to 0. Now if we have this equal to 0 and all of these are equal to 0, then that will be linearly independent. So linearly independent is where we have this equal to 0 implies all the c have to be 0. Right. Okay. The easier way to determine if they are linearly independent or not is to use wrong skin, and that's with the theorem. If we have the set of functions and if they are linearly independent, if the wrong skin is never 0 on that interval, or it is non-zero at some point that contained in the interval a, b. Right. So mostly we use the last one. As you see, we will use, have some example later. Right. Now, here's some example. The set of this function are linearly independent. So 1, x squared, all the different power of x are linearly independent. Cosine x, cosine 2x, cosine 3x, all of those are linearly independent. And exponential function with different coefficient on the exponent are also linearly independent. Now let's look at some example. Determine if the set of these three functions are linearly independent. So what we need to do is just find the Wronskian and see how to go from there, right? So the Wronskian of three functions the variable is x, right? So we just have f1 prime, f1 double prime, f2 prime, f2 double prime, f3 prime, f3 double prime. Now we will write out the function. So on the function and on the derivative, on the second derivative, that make a 3 by 3, find the determinant. That gives us the Wronskian. Right, so x squared plus 1, derivative 2x, derivative of 2x, 2. That's the first one. Second, negative x plus 2, derivative negative 1, derivative 0. Next, 2x squared plus x, derivative 4x plus 1, and derivative again is 4. Right, so we have a 3 by 3 determinant. To evaluate 3 by 3 determinant, there's a good thing of like 5-6 different ways on the top of my head, but the easiest way we do that is using the cofactor or cofactor expansion or minor. Right, meaning that we're going to pick any row or any column. Any row or any column will work, but have to consider the sign chart. So the sign chart is just like a chessboard. This is 3 by 3, right? So we start from a plus, and it's just like a chessboard, alternating sign. Now we'll pick any row or any column. And the way we do that, we'll pick the row and the column that has the most 0, because that will be easier. So I can choose the second row, second column, or the last row. Here I will choose the last row. Right, we have those elements 2, 0, and 4. Of course, pick the one with the most 0. Now, first we have a 2. Right, that number 2. The 2 is sitting on the plus sign. So we have plus. Once we determine that, we'll cover the row and the column containing the element 2. So I cover the row and the column that containing the 0, the 2. So cover the row and the column. Alright, what's left? What's left is the 2 by 2, right? Minus x plus 2 to x squared plus x minus 1 for x plus 1. So that is the first entry. The next entry on the row that we choose is 0. 0 sitting on the minus sign, so minus. And then cover the row and column that containing the 0 entry. What's left is x squared plus 1 to x squared plus x to x, and for x plus 1. Of course, that's just a 2 by 2 determinant. Last one is 4, and 4 sitting on the plus sign. And then cover the row and the column that containing 4. We have x squared plus 1 minus x squared minus x plus 2 2x minus 1. Now we just have a 3 by 3, I mean a 2 by 2 determinant. Right, now if we have a 4 by 4 determinant, we can choose any row or any column. We break down the 4 by 4 into 4 3 by 3s, and then for 3 by 3s, we break down to 3 2 by 2s. So the only thing we need to do is a 2 by 2 determinants. Anything higher than that, we can always break down all the way to 2 by 2. Right, so first there's a 2. Now multiply this out. Run out of space here, so I try to multiply this. Negative x plus 2 times 4x plus 1. Negative x plus 2 times 4x plus 1. That negative 4x squared. Negative x plus ax plus 2. So negative 4x squared plus 7x plus 2. Right. Negative 4x squared plus 7x plus 2. Right. And then, of course, for 2 by 2 determinant, we multiply this and we subtract the other direction, right? So here we subtract the other direction. So subtract negative 1 times 2x squared plus x. That gives us 2x squared plus x. Right. Next, minus 0. Now the nice thing about 0 is doesn't matter what it is inside. It will be 0. Next, there's 4. X squared plus 1 times negative 1. Negative x squared, negative 1. And then the other direction is opposite. So we have negative 2x and negative x plus 2. So that gives us negative 2x, so negative 4x squared. Sorry, negative 2x squared. Never mind. Okay. So we have 2x times that, but with the negative. So 2x times that is 2x squared minus 2x times 2 is minus 4x. So plus 2x squared. Yeah, multiply that with the negative. Minus 4x. Right. Now try to simplify this. Negative 4x squared plus 2x squared. So that is negative 2x squared times 2 negative 4x squared. Right? By like terms, 2x negative 2x squared times 2 negative 4. 7 plus 1 is 8 times 2 is 16. So we have 7x plus x. That ax times 2, 16x. 2 times 2 is 4. And multiply this out. Negative x squared, 2x squared. That gives us x squared times 4. 4x squared. Negative 4x times 4, negative 16x. And 4 times minus 1, minus 4. Now we have negative 4x squared, cancel with 4x squared, 16x, cancel with negative 16x, 4 minus 4. So this is pretty much equal to 0. Now it is equal to 0 for every x. Because it is equal to 0, they are not linearly independent. Or we say because it's equal to 0, it is linearly dependent. Right. because the Wronskian equal to 0. Now, according to the definition, if it is linearly dependent, meaning one of them can be written as a linear combination of the others. So because of that, let's say if we have f1 equal to x squared plus 1 and f2 equal to negative x plus 2. Let's say we're trying to get to x squared plus x. We're going to need 2x squared, right? So why we multiply 2 on that? So that gives us 2f1 equal to 2x squared plus 2, right? The next one, we need to have positive x. So in order to get positive x, we will multiply negative 1 here. So that gives us negative f2 equal to x. 2 times minus 1 is minus 2. Now if we add side by side, we have 2f1 minus f2 equal to 2x squared plus x. 2 and 2 cancel out. By the way, 2x squared plus x, that is f3. So what we show is f3 can be written as a linear combination of f1 and f2. Because of that, they are linearly dependent. f3 can depend on the other two. That kind of thing like that. So they are not linearly independent, or they are linearly dependent because the Wronskian equal to 0. Right. Now, try similar thing on the next one. Is the set of these three functions linearly independent function? So of course we just find the Wronskian again. So Wronskian equal to, now we just put three functions. The function derivative again, sine x. Derivative of sine x is cosine x. Derivative of cosine is negative sine. And then we have cosine, negative sine, and negative cosine. Right. We can pick any row or any column. Since all of them have e to the x, and none of them 0, so that's difficult to choose the row or column. But of course we can choose anything, right? And we choose the first column here. Just do this. Yeah. So we expand using the first column. First, we have e to the x. That entry sitting on the plus sign. After that, we will cover the row and the column that containing that entry. And then we write what's left, which is a 2 by 2. Cosine x minus sine x minus sine x minus cosine x. And then next we have e to the x here. Once again, cover the row and the column that containing e to the x. So it is that. This e to the x sitting on the minus sign. Yeah. And what's left is of course a 2 by 2 sine x cosine x negative sine x negative cosine x. And then the last one also e to the x. Also e to the x, but the last one sitting on the plus sign. Cover the row and the column that containing that e to the x, we have sine x cosine x cosine x negative sine x. Right. Now we have a bunch of 2 by 2 determinant. First e to the x. For this 2 by 2, multiply give us negative cosine square. And then sine square, but this direction is negative. Next, e to the x. Sine times negative cosine is negative sine x cosine x. And that negative, but that direction is negative, so we're going to plus sine x cosine x. And then plus e to the x. Sine times negative sine square, negative cosine square. Right, cosine square plus sine square is 1. And that is Pythagorean identity. So this negative cosine, negative sine square is negative 1. So we have e to the x times negative 1. Sine x cosine x, sine x cosine x, the middle term cancel out, so this go to 0. And we just have e to the x. Once again, that gives us negative 1. So we end up with negative 2 e to the x. Now, exponential function. Y equal to e to the x. That's going to be positive for every x. So what we have here, this is not equal to 0, right? Yeah, because we have something that is not equal to 0. Of course, if it's greater than 0, it is not equal to 0. Multiplied by negative 2 is not going to be equal to 0. Since the Wronskian is not equal to 0 for every x. We say the set of these three functions are linearly independent. Linearly independent. Right. So if Wronskian equal to 0, linearly dependent. If it's Wronskian not equal to 0, it's linearly independent. Right. Now, suppose we have three functions. We have a set of functions are linearly independent. Then we call that is the fundamental set of solution. Right. Now this is nothing new. Remember, if we have all the solutions are linearly independent, then we just write the solution as a linear combination of all of them. Right. Now, if they are not linearly independent, meaning one of them can be written as a combination of the others. So that's why we don't need all of them. Right. Let's say y sub n can be written by the rest of the function, then we don't really need that. So that's why the solution is not in that form. So the solution in this form, if all of them are linearly independent function, or we call that is the fundamental set of solutions. So here we have function that is fundamental set of solution, meaning that linearly independent. Then we can write the solution as the linear combination of all of those functions. So that is the homogeneous equation when that equal to 0. If we have the input function and we have a particular solution, that's why the P is a linear is a particular solution. Then we're going to have those complementary solution, and then plus particular solution. So that's nothing new. Now we just extend this into the set of a bunch of function more than 2. So we might have the equation, a differential equation of the higher order than 2, and it still work. If we have the set of linear combination, if we have the set of linearly independent function as a solution, then we just write that as a linear combination. If we want a non-homogeneous equation, try to come up with a particular solution, adding that particular solution to it, we have the general solution. Right, so now this just a little more general than what we learned in chapter 4, but the idea is still the same. I stop the video here. As always, thank you for watching.